Welcome. If you've ever wanted to get into programming but had no idea where to even begin, you are in the perfect spot. Over the next few minutes, we're going to pull back the curtain on the Python language, and believe it or not, you'll write your very first program. So let's just dive right in.
Okay, so let's start with the most basic question of all. How in the world do you actually tell a computer what to do, right? It doesn't understand English, so we need a special language to communicate with it. And really, that's all programming is. It's just the art of giving a computer a set of instructions it can actually understand and follow.
And that is exactly where Python comes in. It's one of the most popular programming languages on the planet for a reason. It's a fantastic bridge between the way we think and the way computers work. It was literally designed to be easy to read, super powerful, and a great first step for anyone who's new to coding.
And get this, it's not some new fad that just popped up. Python's actually been around since 1991. That means it has decades of history. It's been tested, it's been refined, and it's been improved over and over, which is what makes it such a solid and reliable tool today.
But what is it that makes this language so special? I mean, why is it the go-to for giant companies like Netflix or even for scientists at NASA? Let's break down the main reasons for its worldwide popularity.
Well, first and foremost, its code is just incredibly clean and easy to read. A lot of the time writing Python feels more like writing a simple sentence in English than it does writing complex code. This makes it way less scary for beginners because you can focus on the what you want to do, not on memorizing a bunch of confusing symbols.
Another huge reason is that Python is totally free and open source. You don't have to go out and buy some expensive software license to use it. Anyone, anywhere on Earth can download it and just start creating things. This has been absolutely crucial for building its massive global community.
Python is also what we call cross-platform. So what does that mean? It just means you can write a program on a Mac, and that exact same code will run perfectly on a Windows PC or a Linux machine, no changes needed. It's this write once, run anywhere idea that developers just absolutely love.
And with Python, you're never really alone. There's this huge global community of people who are constantly helping each other out. And all that teamwork has created this amazing collection of libraries. You can think of them like toolkits of pre-written code. So let's say you need to build a website or create a complex chart. Odds are there's a library for that, which lets you do it in just a couple of lines.
And this is where Python's true power really shines. Its versatility. It is not just for one thing. It's the engine behind web applications, it's the brain behind AI and machine learning, and it's the #1 tool for data scientists. You could even use it to automate boring tasks on your computer or build your own video games. It is, quite literally, everywhere.
Okay, so we've talked a lot about what Python is. Now it's time to actually use it. Let's walk through the steps to get Python up and running on your machine so you can write your very first program. It's your turn.
First up, you've got to install it. Just head over to python.org, grab the latest version for your computer, and run the installer. Now, here is a really, really important tip. During the installation, make sure you check the little box that says Add Python to Path. Trust me on this one. It just tells your computer where to find Python, and it'll save you a ton of headaches down the road. Okay, once it's installed, Python gives you a simple little editor called idle. All you have to do is open it up, type your code right in there, and then run it. It's a simple 3-step process to bring your very first instruction to life.
And this is it. This is your entire first program. It's just one line. That print command is a basic fundamental piece of Python. It's a simple instruction that tells the computer, hey, display whatever text I put inside these parentheses and quotes on the screen. That's all it is.
And when you run that code, this is what you'll see. Hello, Python! And that is the heart of programming right there. You wrote an instruction, and the computer followed it perfectly. So, congratulations, you are officially a Python programmer.
So, you saw your code work, but how did it actually work? Let's take a quick peek behind the curtain and look at 2 of the most important rules that Python follows to understand what you're telling it to do. The first thing to know about is the interpreter. When you run your program, a special piece of software called the Python interpreter reads your code, one line at a time, and translates it into instructions the computer's hardware can actually execute. It's kind of like having a personal translator who reads your script and tells the machine what to do, line by line.
All right, this second rule is a little bit unique to Python, and it's super important. Indentation. Those spaces at the beginning of a line, they're not just for making the code look pretty, they're actually part of the language's grammar. They tell Python which lines of code belong together as a group. So here, that indented print statement, it belongs to the if statement right above it. It's how Python keeps everything organized and easy to read.
And there you go. In just a few minutes, you've installed Python, you've written your first command, and you've seen it work. You've officially taken the first and, honestly, the most important step on a much bigger journey. So, what's next?
I mean, think about it. Today, you learned how to make a computer say hello. Tomorrow, you could be building a website or analyzing data, or maybe just automating some boring part of your job. You've now spoken your first words to a computer. The only real question left is, what are you going to build next?
All right, let's get right into it. Today, we're going to break Python down to its absolute bare bones. My goal here is that by the end of this, you'll totally get the fundamental building blocks, the essential pieces you need to write your very first program. So, let's dive in. So, what does it actually take to write a program? You know, it really just boils down to 3 core ideas. And I want you to keep this question in the back of your mind because everything we're about to cover is going to lead us right back to this answer. So here's our game plan. We're going to start with Python's special words, kind of like its vocabulary. Then we'll see how to store information using variables. After that, we'll figure out how to get your code to talk to you and you to it. We'll touch on the grammar of Python. And finally, the best part, we'll put it all together and actually build something. First things first, let's talk about the actual words Python understands. Just like English or any other language, Python has its own vocabulary with special meanings, and it also has rules for how you can make up your own names for things. Okay, so Python keeps about 35 special words for itself. These are called keywords. You can think of them as reserved commands that Python needs to do its job. Words like if, true, and else, they already have a specific meaning, so we can't use them to name our own stuff. They're off limits. So if we can't use those keywords, what can we use? Well, we get to create our own names, and these are called identifiers. And the rules are super simple, really. Your names have to start with a letter or an underscore. That's it. They can't start with a number, and they can't have spaces or weird symbols in them. That's why something like roll_no is perfectly fine, but hello world just won't fly. Okay, so we know how to name things, but what are we actually naming? We're naming variables, and this is our second big building block. It's how we store and manage information inside our programs. Honestly, the best way to think about a variable is just as a labeled box. That's it. It's a container. You put a piece of data inside the box, and you slap a label on the outside so you can find it again later. That's all a variable really is. Let's make this real for a second. Look at this line. We're taking a piece of text, the string Rahul, and we are putting it inside a container that we've decided to label name. That equal sign, just think of it as an arrow that means put this value into this box. We're assigning the value to the variable. Simple as that. So what kind of stuff can we actually put in these boxes? Well, a whole lot, but for right now, here's a quick peek. They can hold whole numbers, which we call integers, or int. They can hold numbers with decimal points, which we call floats. Of course, they can hold plain old text, which we call a string, or str, and they can hold a simple logical value, true or false. We call that a Boolean, or bool. All right, you see how this is starting to stack up? We have our containers, we know what they can hold, but how do we get information from a user? And just as important, how does our program talk back to them? To get information from a user, we use a built-in command called the input function. A function is just a reusable piece of code that does a specific job. This one tells the program, hey, pause for a second, show this message on the screen, and then wait for the user to type something. Whatever they type gets stored right into our name variable. It's our direct line to the user. And to talk back, we use the print function. This is the program's voice. It takes whatever you put inside the parentheses and displays it on the screen. So here, it's going to show the word welcome, and then whatever value is currently tucked away inside that name variable. Okay, on to our third and final crucial piece of the puzzle, the grammar. Just like human languages have grammar to give them structure, Python has rules that tell it how all the different pieces of code are connected to each other. Now, this is a big one. A lot of other programming languages use things like curly braces to group code into blocks. Python does it differently. It uses indentation, literally the white space at the beginning of a line. And this isn't just to make the code look pretty, it's a mandatory rule. That white space actually defines the structure of your program. Take a look at this. See how the print statement is pushed in by 4 spaces? That little indent is everything. It's telling Python that the print command belongs to the if statement right above it. It's part of that block. It will only run if that condition is true. That space, that is the grammar. Now, here's a really useful little grammar rule. Remember that input function? Well, it has a quirk. It always gives you back text, a string. Even if the user types in the number 5, Python sees it as the character 5. So, if you want to do math with it, you first have to convert that text into a number using a function like int. We call this process casting, and it's super common. And one last quick thing. What if you need to print something that's kind of tricky to type, like you want to start a new line, or you need to put a quote mark inside your text? For that, we use these things called escape characters. It's just a backslash followed by another character, like /n for a new line that acts as a special command inside your text. All right, deep breath. We've covered the words, the containers for our data, how to communicate, and the grammar. We have all our building blocks. Now it's time to put them together and actually write some code. Let's start with the absolute simplest version. We create 2 variables, a and b, we put some numbers in them, and then we just use our print function to show the result of adding them together. Easy enough, right? Okay, let's step it up and make it interactive. This time we use our input function to ask the user for their name and we store their answer. Then we use print to greet them personally. You see how we're combining those blocks now? Input and output, working together. And now, for the grand finale. This little program puts everything we've learned together. We use input to ask the user for a number. We use int to cast that text into a number we can actually use for math. Then, we do a simple calculation, side times side. And finally, we print the result. All the pieces are here. And that's really it. Those are the fundamental pieces. You now get how to store data using variables, how to talk back and forth with the user using input and output, and how Python's grammar and structure hold it all together. You officially have the core building blocks. You've taken that first, most important step. You've seen how these really simple ideas can combine to create a real working program. So really the only question left is, now that you've got the basics down, what are you going to build next? Have you ever just stopped and wondered how Python knows what to do with the stuff you give it? Today, we're going to pull back that curtain and look at one of the most important ideas in all of programming, data types. You can think of them like the Lego bricks for your code. They're the basic pieces you're going to use to build literally anything you can dream up. So let's start with a really simple question. When you type the number 10 into Python, how does it know that's something you can do math with? And then when you type hello, how does it know that's a word and you can't just, add 5 to it? Well, the secret to all of this is a concept called data types. The easiest way to think about a data type is to imagine it's a label. It's a label that tells Python 2 super important things. First, what kind of information you're storing, and second, what kinds of things you're allowed to do with that information. I mean, it makes sense to add 2 numbers, right? But it makes 0 sense to try and divide your name by 10. Data types are the rules that make sure our code actually works. All right, so here's our little roadmap for the next few minutes. We're going to go on a quick tour of the most common data types you'll run into in Python. We'll start with the simple stuff and work our way up. We'll cover numbers, text, logic, and even how you can group all that stuff together. Ready to dive in? Let's get started with the basics. Okay, first up are the types that are the most intuitive, the ones you already use in your daily life without even thinking about it. We're talking about text, numbers, and some simple yes or no logic. First on our list are integers, or int for short. These are just your classic whole numbers. No fractions, no decimals, nothing fancy. Think about things you can count, right? Like the number of people in a room, your age, or the score in a game. If it's a solid, whole number, chances are it's an integer. And here's exactly what that looks like in code. When you write something like a equals 10, Python looks at that 10, sees it's a whole number, and instantly knows, aha, that's an integer. It really is that simple. But what about when you need to be a bit more precise? That's where floats come into play. A float, or a floating point number, is basically any number that has a decimal point. So think about the price of your coffee, a temperature, or any kind of scientific measurement that needs that extra bit of detail. So for example, if you were to write pi equals 3.14, Python sees that little dot, that decimal point, and immediately knows that you're working with a float. This is what lets you handle much more precise calculations. Okay, we've covered numbers. Now, what about text?
In Python, we call this a string, or str. A string is just any sequence of characters that you wrap up in quotes. It could be one letter, one word, a whole sentence. It doesn't matter. This is how you're going to handle all of your text data.
Now, this is where things get really cool. Python doesn't just see a string as one big blob of text. It sees it as a sequence of individual characters, and each one has its own position, which we call an index. And here's a little secret of programming. We always start counting from 0. So in the word Python, P isn't at position 1, it's at position 0. Y is at 1, and so on. Trust me, this little detail is going to be super important later on. All right, the last of our basic building blocks is the Boolean. Now, it sounds kind of fancy, but it's probably the simplest of them all. A Boolean can only ever be one of two things, true or false. That's it. Think of it like a light switch. It's either on or off. It's the simple yes or no that lets your program make decisions. Now, you're not usually going to be typing true or false yourself. Instead, you'll get them as the result of a comparison. So, for example, if you ask Python, hey, is 10 greater than 5? Python will look at that, think for a millisecond, and give you back the Boolean answer, true. So we've got our basic building blocks, numbers, text, and Booleans. But what happens when you want to store a whole bunch of them together? That's where collections come into the picture. Let's take a look at how Python groups things. Okay. Let's look at two ways to store a sequence of items, lists and tuples. Now, they look really similar, but there's one huge difference. A list is like a shopping list. You can add items, you can cross things off, you can change your mind. It's flexible. But a tuple is like a rule that's been carved into stone. Once you create it, you cannot change it. And believe it or not, that's a good thing. You use tuples for data that you know should never, ever change, which makes your code a lot safer and more predictable. Next up is one of my personal favorites, the dictionary. You see, unlike lists and tuples, dictionaries don't really care about the order of things. Instead, they work with key value pairs. And it's exactly like a real dictionary. You have a word, that's the key, and you have its definition, that's the value. This makes them absolutely perfect for storing related pieces of information. And here's a perfect example of how that works. Let's say we're storing a student's info. If you want to find out their name, you don't have to remember if it was the first or second item in a list. Nope, you just ask the dictionary, hey, what's the value for the key, name, and boom, you get back Aman. It's a much more logical and human-readable way to organize your data. All right, we've covered the main players. Now let's quickly peek at a couple of specialized tools that you'll use for very specific jobs. So let's talk about sets. A set is a collection that has a very special superpower. It only allows unique items. It absolutely hates duplicates. It's also unordered, so there's no first item or last item. The main reason you'd ever use a set is to very quickly and easily get rid of any duplicates in your data. Just check this out. We're trying to create a set here with 2 3s in it. But look at the result. Python automatically sees the duplicate and just throws it out. It's an incredibly powerful tool for when you need to clean up your data and find only the unique things in it. So you've learned about all these different data types. That's great. But you might be wondering, why does this actually matter? Well, this is where the rubber meets the road, because sometimes you get data in the wrong format, and you need to know how to fix it, or at least check what it is. So imagine this common scenario. You ask a user to enter a number, and they type in 5. But that number comes into your program as text, as the string 5. It looks like a number, but to Python, it's just a character. You can't do any math with a string. If you tried to add 5 to this, your program would just crash. The solution to this problem is something called typecasting. This is where we explicitly tell Python, hey, I know this looks like text, but I want you to convert it into a number. By using the int function, we can literally transform the string 5 into the integer 5. Now, it's a real number, and we can finally do our calculations. This is a skill you are going to use all the time. And what if you're not even sure what kind of data you're working with? Maybe your code is breaking and you have no idea why. Well, this is where the type function becomes your new best friend. Think of it as your own personal data detective. You can wrap any variable in type function to ask Python, hey, what kind of data am I actually looking at here? It's an absolutely essential tool for debugging your code. So there you have it. Those are the fundamental building blocks of Python. We've gone from simple numbers and text all the way to powerful collections like lists and dictionaries. These are the tools that you will use to create anything and everything you can imagine. Now that you've got the tools, the only question left is,
What will you build first? All right, welcome. Today we are diving deep into the essential action words of the Python programming language, operators. These are the symbols that are going to turn your static data into a dynamic working program. So let's just start with a really fundamental question. If variables are the nouns in our code, they're the things that hold information, what are the verbs, right? How do we actually make things happen? Because think about it. You can have all the data in the world stored in your variables, but on its own, it's totally static. It just sits there. To make any of it useful, you have to perform actions on it. And that is exactly where operators come in. They are the true verbs of your code, those special symbols that perform actions on your data and really bring your entire program to life. Okay, so let's get just a little bit more formal for a second. An operator, simply put, is a symbol that tells the computer to do a specific job, whether that's something mathematical or relational or logical, on one or more values. And those values, we just call them operands. So we're going to start with the absolute essentials. I want you to think of these as the hammer and the screwdriver of your programming toolkit. These are the operators you are going to find yourself using all the time. First up, the arithmetic operators. Now, these are your old friends from math class, right? Addition, subtraction, multiplication. But Python gives us some really powerful extras, like the double asterisk for exponents, so 2 to the power of 3, and the percent sign for modulus. That's just a fancy way of saying, hey, give me the remainder after you do the division. Now, here's something really important. Python makes a crucial distinction between two types of division, and this is something that often trips up beginners. A single slash slash gives you the exact answer, decimals and all, but a double slash slash slash, that performs what's called floor division. It basically just chops off the decimal and gives you only the whole number. Next up, assignment operators. The simple equals sign is the most basic one. It just assigns a value to a variable. But we also have these incredibly useful shortcuts, these compound operators, like plus equals plus equals. This is such a clean way to add a value to a variable and update it in a single step, instead of having to write out the whole x equals x plus 5. The final piece of our core toolkit is comparison operators, and their entire job, their whole reason for being, is to compare two values and then answer a very simple direct question with either a true or a false. And these operators, they are the absolute foundation of making decisions in your code. Is this value equal to that one? Is it greater? And hey, pay close attention to that double equals sign for checking if things are equal. A single equals is for assignment. This simple true or false answer is what tells your program which path to take next. Okay, so we can now ask simple true or false questions. But how do we combine them? How do we build more complex, more intelligent logic into our programs? Well, this is where logical operators come into play. These three keywords, and, or, and not, are like the glue that lets you create these really sophisticated decision-making paths. And means everything has to be true. Or means just one thing needs to be true. And not, well, not just flips the result completely. So, for example, let's say you want to check if a number falls within a specific range. You don't have to do two separate checks. You can combine them with the AND operator to ask one single powerful question. Is this number both greater than 5 and less than 20? All right, moving on. Beyond those daily essentials, Python also has this set of specialized operators. Now, you might not use these every single day, but for certain specific jobs, they are incredibly powerful and super efficient. So here's a common problem. How do you check if a specific item exists inside a collection, like a list of names or maybe words in a sentence? I mean, you could write a loop to check every single element one by one, or you could just use a membership operator. The in and not in operators they're beautifully simple. They look right into a sequence for you and spit back a straightforward true or false answer if that element is found. It makes your code so much cleaner and easier to read. Okay, listen up, because this is a crucial distinction, and it's a classic gotcha for new programmers. The difference between equals equals and the is operator. They look similar, but they check for two very different things. So on the left, equals equals checks if the values are the same. We've got two lists, x and y, and they both contain the numbers 1 and 2. The contents are identical, so x equals y is true. Makes sense.
But on the right, the is operator checks if they are the exact same object in memory. Think of it this way. Equals equals checks if two houses look identical. Is checks if they have the same street address. In our code, X and Y are two completely separate lists that just happen to look the same. They're not the same object, so X is Y is false. It's a subtle but really powerful difference. And finally, let's just quickly touch on bitwise operators. We are not going to go deep here, but it is good to know that they exist. They let you work directly on the binary digits, the zeros and ones, that actually make up a number. This is a very specialized tool, but it's incredibly fast for things like low-level graphics, data encryption, or network programming, anywhere you need to fiddle with the raw bits of information. Now, let's talk about what might be the most important rule of all. Just like grammar in a sentence makes sure it has the right meaning, Python has a strict order for evaluating operators. This is to make sure your calculations are always predictable and correct. We call it operator precedence. Take a look at this expression on the screen. 2 plus 3 times 4. Now, if you just read that from left to right, you might think the answer is 20, right? Because 2 plus 3 is 5, and 5 times 4 is 20. But is that what Python does? As you're about to see, the order really, really matters. See, Python follows a very clear hierarchy, just like you learned back in math class. It will always resolve anything in parentheses first, no exceptions. Then it handles exponents. After that comes all the multiplication and division stuff, and only at the very end does it do the addition and subtraction. So this right here is why the correct answer is 14. Following those rules of precedence, Python calculates the multiplication, 3 times 4, first. That gives it 12. And only then does it perform the addition, adding 2 to get that final result of 14. And there you have it. Those are the action words of Python. We've gone through everything from basic math and assignment all the way to complex logical decisions. You now have the fundamental tools you need to take data and make it come alive. So the only question left is, what are you gonna build first? Hey everyone, if you've ever typed a password, sent a text message, or even just searched for something online, then you've been working with strings. Today, we are opening up the Essential Python Toolbox to show you exactly how to master them. Let's jump right in. You know, to us, we see words, sentences, whole paragraphs. It all makes sense, but to a computer, it's all just data. So how in the world does Python take something as simple as hello world and actually make sense of it? Well, that's the core question we're going to answer today. We're going to build your string manipulation toolkit completely from the ground up. First, we'll look at the blueprint, what strings actually are. Then we'll grab our precision tools for accessing specific parts. After that, we'll fire up the power tools, all those essential functions. We'll also cover the workshop rules you just can't break. And finally, we'll put it all together with some really practical examples. Okay, let's start with the absolute basics. Before you can build anything cool, you have to understand your materials, right? So first things first, what exactly is a string? It's really that simple. Anytime you see text inside your Python code, you are looking at a string. It's just an ordered sequence of characters. Could be a single letter, a person's name, or, hey, even an entire book. It's Python's fundamental way of handling text. And creating one is incredibly easy. You can use single quotes, or you can use double quotes. Honestly, Python doesn't care. It treats them exactly the same. But what's really cool is this third option, triple quotes. This is your secret weapon for any text that spans multiple lines. Think about a long paragraph, or maybe a big chunk of code from another language that you want to store. Triple quotes are perfect for that. All right, so now that we know what a string is, let's grab our precision tools. This is where we learn how to zoom in on just one character or neatly cut out a specific piece of text that we need. So here's the deal. Every single character in a string has an address. We call it an index. And in Python, like in a lot of programming, we always start counting from 0. So in the string Python, P is at index 0, Y is at index 1, and it just goes on from there. This is how you pinpoint any character starting from the beginning. But what if you want the last character? I mean, you could find the length of the string and then subtract 1, or you could use this brilliant shortcut called negative indexing. You just count backward from the end, starting with -1. So S-1 will always give you the last character of any string, no matter how long it is.
Super, super useful.
Now, what if you want more than just one character? That's where slicing comes into play. Using this start-end format, you can cut out a piece of the string. Now, here's the one crucial thing to remember. It grabs everything up to, but not including, that end index. So 0, 3 gives you characters 0, 1, and 2. Oh, and if you leave one of the numbers out, Python just assumes you want to go all the way to the beginning or all the way to the end.
Okay, we've handled the precision work. It is time to bring out the power tools. These are the built-in functions that let you totally transform and analyze strings with just a single command. Let's run through some of the greatest hits.
First up, len. Need to know how long a string is? Just wrap it in len it. It's fast, it's simple, and trust me, you are going to use this all the time.
Need to shout your message? The .uppercase method instantly converts every single character to uppercase. And as you can probably guess, there's a .lowercase method that does the exact opposite.
Oh man, this one is an absolute lifesaver. When you get text from a user or a messy data file, it often has these extra pesky invisible spaces at the beginning or end. .strip cleans all that junk up instantly, preventing all sorts of weird bugs down the line.
The replace.replace method is basically your search and destroy tool. It finds every single instance of one piece of text and replaces it with another. It's incredibly powerful for cleaning and standardizing your data.
Now, these two, they're a dynamic duo. .split takes a string and shatters it into a list of smaller strings based on some separator, like a comma. And .join does the exact opposite. It takes a list of strings and glues them back together into one single string. You'll be using these together constantly.
Look, every workshop has safety rules, right? The string workshop is no different. If you don't get these fundamental properties, you're just going to run into frustrating errors. So let's cover the essentials you need to know.
You can actually do some simple math-like things with strings. The plus sign smashes them together. We call that concatenation. The multiplication sign repeats a string a bunch of times. And the in keyword is just a super quick way to check if a little string exists inside a bigger one. It just gives you back a true or false. So this leads to a really logical question. We know we can use an index like s sub 0 to read the first character of a string. So it seems like we should be able to use that same index to change it, right? Well, let's just try it. If we take the string hello and we try to change that first character to a B, we get an error, a type error to be exact. So why? What's going on here? This right here perfectly demonstrates the single most important rule about Python strings. And here it is, the golden rule. Strings are immutable. Now, that's a fancy word, but all it means is they cannot be changed. Once a string is created in Python, it is set in stone. So if you want to change a string, what you're really doing behind the scenes is creating a brand new one from scratch. Okay, we have filled our toolbox, and we've learned the rules of the workshop. Now for the really fun part. Let's combine these simple tools to solve some actual common programming problems.
So, how would you count the number of vowels in a word? We can combine our tools. First, we'll start a counter at 0. Then, we'll loop through every single character in our string. And for each of those characters, we use that in operator we just learned to check if it's one of the vowels. If it is, boom, we just add one to our count. See? Simple tools, powerful result.
And that brings us to one of the most elegant, most famous little tricks in all of Python. It really goes to show that sometimes the simplest looking solutions hide the most power. How do you reverse a string? I mean, you could write a complicated loop, or you could just do this. s/-1/. It's a special kind of slice that basically says, start at the end, go to the beginning, and step backward one character at a time. It is concise, it is beautiful, and it's just a perfectly Pythonic way to solve the problem. It really makes you wonder, what other clever combinations can you build with the tools in your new string toolbox? All right, today we're going to do something really cool. We're going to give our code a brain. Yeah, you heard me. We're not just writing a blind set of instructions anymore. We're going to teach our programs how to think, how to evaluate a situation, and how to make a choice, just like we do all day, every day. I mean, have you ever really stopped to think about it? How does a game know you've leveled up? Or how does an app decide whether to show you the login screen or your personal dashboard? It's not magic, right? It's all about logic. It's the program making a decision right then and there.
Okay, so let's get into it. We're about to unlock one of the most fundamental powers in all of programming, giving our code the power of choice. And the way we do that is with something called conditional statements. Seriously, these are the absolute core building blocks for any piece of code that you could call smart. So what are these things really? Well, at their heart, conditional statements are basically just questions. The code asks, hey, is this particular thing true? And if the answer is yep, the program does one thing. If the answer is nope, it does something else, or maybe nothing at all. But that's the key, right? It's all about checking a condition and then acting on whatever the answer is. So we're going to start with the simplest, most essential piece of the puzzle. This is the foundation for all decision-making in code, the if statement. Everything else we talk about today is going to build right on top of this one simple idea. Before we even touch a line of code, let's think about this in a way we all get. Imagine a simple rule. If you are 18 or older, you can vote. See? The condition is your age and the action is being able to vote. It's a straight-up, one-way street. If you don't meet the condition, let's say you're 17, then that specific rule just, well, it doesn't apply to you. Simple as that. Okay, now let's see how Python's syntax mirrors that real-world logic almost perfectly. On the left, you've got the general structure, and on the right, you see our voting rule turned into actual code. We start with the keyword if, then we put our condition, age is greater than 18, and then we end it with a colon. Now, this is super important. That line below it is indented. That little bit of space tells Python, hey, only run this action, the print statement, if that condition is true. And just like that, you've created a direct cause and effect relationship. The condition was true, it got the green light, and boom, the program printed the message. It's really as straightforward as it looks. But that brings up a pretty obvious question, right? What happens if the condition is false? In that last example, if the age was 17, the program would just, well, do nothing. It would just skip that line and move on. And, that's not always what we want. Sometimes you need a plan B. And that is exactly where the else statement comes into play. Just think of else as the word otherwise. It literally gives the program an alternative path, something else to do when that initial if condition fails the test. So check this out. This creates a really clear fork in the road for our program. It gets to a decision point. If the condition is true, it goes down one path. But if it's false, it goes down the other. And here's the crucial part. The program has to take one of these two paths. It can never, ever take both. Okay, so we've got a plan for if this happens and a plan B for otherwise. But let's be real, life isn't always that simple, is it? What if you've got more than two possibilities? Like, think about assigning a letter grade based on a score. A simple if-else just isn't going to cut it. To solve this, we use something that's often called an if-elif-else ladder. And elif is just a short, convenient way of saying else if. Here's how it works. The program starts at the very top and checks that first if. Are the marks 90 or above? If yes, awesome. It prints grade A and jumps off the ladder completely. It's done. But if not, it moves down to the next rung, the first elif, and asks, okay, well, are the marks 75 or above? It just keeps going down the rungs until it finds a condition that's true, runs that code, and then it's out. And that else at the very bottom, that's our catch-all. It's for anything that didn't meet any of the other conditions. All right, so we've got the basic structures down. If else, and that if-elif-else ladder. Now, let's talk about the tools that make the conditions themselves way more powerful and precise. Think of these as our power-ups. First up, we have our comparison operators. These are the little symbols we use to actually ask the questions. And you gotta pay attention to the double equal sign for checking if two things are equal. That one trips up beginners all the time. A single equal sign is for assigning a value, double is for comparing. Then you've got not equal, greater than, less than, you get the idea. These are basically the verbs of our conditional sentences. Next up, logical operators. These are awesome because they let us combine multiple checks into one single, powerful condition. You've got and, which is the really strict one. Both sides have to be true for the whole thing to be true. Then there's or, which is way more chill. As long as at least one side is true, the whole thing is true. And finally, not, which just flips the result on its head, turning true into false and false into true. Let's look at a perfect real-world example. To be a teenager, your age has to meet two conditions at the same time, right? You have to be older than 10, and you have to be younger than 18. The AND operator is the perfect tool for this. It lets us chain those two checks together into one clean, elegant if statement.
And, for really complex logic, you can even put an if statement inside another if statement. It sounds a little wild, but it's called nesting. So you might first check if a user is over 18, and if that's true, then you could have another if statement inside that one to check something else, like maybe their subscription level. It lets you make decisions within decisions. All right, let's put all this together. Theory is great and all, but seeing how these tools actually solve real problems, that's when it all really clicks. So let's run through a couple of classic examples. Okay, first problem, you've got a number, and you need to figure out if it's positive, negative, or zero. Right away, you know there are 3 distinct possibilities. This is the perfect job for our if-else-else ladder. First, we check if it's greater than 0. Nope. Okay, next rung. We check if it's less than 0. Still no? Well, if it's not positive and it's not negative, the else block correctly catches it. It must be 0. Super clean, super efficient.
And for our last example, we're coming full circle, right back to where we started, voting eligibility. This is a classic binary choice. A person is either eligible or they're not. There's no in-between. So a simple, powerful if-else handles this perfectly. 1 condition, 2 possible outcomes.
Look, if you take one thing away from all of this, let it be this. Conditional statements are what transform a simple script from just a list of commands into a dynamic program that can actually react and adapt. We've literally given our code a brain. And honestly, that's the most exciting part. You now have the fundamental tool to build whatever you want. Interactive quizzes, simple games, checking if a user typed in a valid email, so much more. The logic is now in your hands. So the only question left is, what are you going to build first? All right, let's talk about something I guarantee you've run into. Have you ever found yourself writing the same line of code over and over and over again? Well, today, we're going to fix that. We are unlocking one of the most powerful and honestly essential concepts in Python, loops. Okay, let's just jump right in. On the left, you see the hard way. You want to print hello 3 times? Fine, you type it out 3 times. It works, sure. But look at the right. That's the smart way. One single, elegant loop does the exact same thing. And that, right there, is why we have loops. It's all about working smarter, not harder. You can think of loops as your first real tool for automation. Seriously, it's how you tell the computer, hey, do this thing a bunch of times, without you having to spell it out every single time. This is a game changer. It saves time, gets rid of all that copy pasting, and makes your code so much cleaner and shorter. So, let's grab our first tool from the toolbox, the for loop. This is your absolute go-to when you know exactly how many times you need to do something. Whether it's 5 times, 1,000 times, or for every single item in a list, the for loop has got your back. Now, the syntax might look a little technical, but I promise, it's super simple. You start with the word for, then you make up a name for a variable. This is just a temporary placeholder. Then you have the word in, followed by some kind of sequence, which could be a list of things, or as we'll see, a range of numbers. And that indented line below, that's the statement, the thing that's going to get repeated. Let's see it in action, because that's the best way to learn. Here, we're saying, for a variable we're calling I, in the sequence range 5. Now, range 5 is just a simple way to generate the number 0, 1, 2, 3, and 4. So the first time through the loop, I is 0, and we print it. The next time, I is 1, and we print that, all the way up to 4. See how that works? Brilliant. And for loops are not just for numbers. This is what makes them so incredibly useful. You can loop through basically any sequence, like this list of fruits. In this example, our variable f becomes apple on the first pass, then banana on the second, and finally mango. It just goes through the list, item by item. So versatile. You know, that range function is so handy, it really deserves its own moment. The simple version, range n, gives you numbers from 0 up to, but not including n. So range of 3 is 0, 1, 2. But you can get fancier. If you need to start somewhere else, range AB starts at A and goes up to B minus 1. And for you power users, you can even add a third number for the step. So range 0, 10, 2 would count up in 2s, 0, 2, 4, 6, 8. All right, time for our second major tool, the while loop. Now, what happens if you don't know exactly how many times to loop? What if you just need to keep doing something until a specific thing happens? Well, that's exactly what while loops are for. The syntax here is, if anything, even simpler than the for loop. It's just while some condition is true, keep on doing the statement. The computer checks that condition before every single pass. The second that condition becomes false, poof, the loop is done. Okay, let's walk through this. First, notice we have to set up our own counter variable, I, and we'll start it at 1. The loop's condition is keep going while I is less than or equal to 5. Inside, we print I, and then, and this is absolutely the most critical part, we increase I by 1. If you forget that I plus equal fuzz1 line, I will always be 1. The condition will always be true, and congrats, you've just made an infinite loop.
So you've got your for loops and your while loops. You're feeling pretty powerful. But what if you need even finer control? What if you need to bust out of a loop early, or maybe just skip a single step? Well, for that, we have 2 amazing commands, break and continue. And this slide lays out the difference perfectly. Think of break as the big red emergency stop button. The second your code hits break, the loop is completely over, done, finished. Continue is totally different. It's more like a skip button on your remote. It just stops the current round and tells the loop, all right, never mind this one, let's just go on to the next item. Let's see that break statement in the wild. This loop wants to count from 0 all the way to 9, but we've put in a rule. If I ever equals 5, hit the brakes. So what happens? It prints 0, 1, 2, 3, 4, but the moment I becomes 5, that if condition is true, break gets triggered, and the whole loop just stops dead. It doesn't even get the chance to print the 5. Now let's compare that with continue. Our rule this time is, if I equals 3, continue. Check out the output. We get 0, 1, 2, but when I hits 3, the continue command says, whoa, skip the rest of this round, which means it skips the print command. But the loop isn't over. It just jumps right to the next number, which is 4, and keeps going. That's why the number 3 is missing from our output. Okay, theory is one thing, but let's be honest, the real fun is seeing what we can actually do with all this. So let's take everything we've just learned and solve a real practical problem. So here's our challenge. We need to find the sum of all the numbers from 1 to 10. Yeah, you could pull out a calculator or do it in your head, but that's that hard way thinking. We're going to do this the smart way, with a loop. And here it is. Look how clean and simple that is. First, we make a variable, s, to hold our total, and we start it at 0. Then we just loop. Our variable I will take on the values 1, then 2, then 3, all the way to 10. And in each step of the loop, we just add the current value of I to our running total, s. And after the loop runs through its 10 steps, what's the final answer? 55. Simple, fast, automated. That is the power you now have with loops. So let's do a super quick recap. What are the big takeaways? First, loops are your best friend for automating repetitive stuff. Use a for loop when you know how many times you need to go. Use a while loop when you're just waiting for a certain condition to be met. And when you need to get fancy, you've got break and continue to give you that fine-tuned control. And I really think this says it all perfectly. With loops, you're not just telling the computer what to do step by step anymore. You're moving beyond that. You're turning tedious, boring, repetitive tasks into elegant, beautiful automation. So now you have these amazing, powerful tools in your programming toolbox. You can iterate, you can automate, and you can control the entire flow of your programs in a whole new way. There's really only one question left to ask. What are you going to build first?
All right, let's talk about giving our Python programs a memory. I mean, wouldn't it be cool if they could actually remember things after we've shut them down? Well, today we're going to unlock that exact superpower. I mean, think about it for a second. You play a game, you crush your high score, you close it, you come back the next day, and boom, your score is still right there. But a normal Python script, it has total amnesia. The second it stops running, everything is gone. So how do we fix that?
And the answer, my friends, is something called file handling. This is the magic that lets our programs talk to the files on our computer. It's how we save that high score, or any data really, and then pull it back in later. It is, quite literally, the long-term memory for our code.
And the key that unlocks this entire world is one simple but incredibly powerful function: open. Every single time you want to read from a file or write to one, your journey is going to start right here.
Now, the best part about this function is just how simple it is. It really only needs 2 things from you. First, the file name, which is just Python asking, hey, which file are we working with? And second, the mode, which is you saying, okay, here's what I plan to do with it.
I love this analogy. Just picture the file as a physical notebook. The mode is just you telling Python your plan.
Are you just going to read what's already there? Or are you going to tear out all the old pages and start fresh? Or maybe just flip to the back and add some new notes?
And that brings us to the three main modes you're going to use all the time. You've got R for read. You're just looking, no harm done. Then there's W for write. And be careful with this one because it erases everything and starts over. And finally, A for append, which just adds your new stuff to the very end, leaving everything else alone. So this is absolutely crucial to understand, the difference between write and append. Using W is like wiping the slate clean before you start writing. It's a destructive action. But A is safe. It just tacks your new data on at the very end. Getting this right is super important. So let's see how this actually works. Once you've got a file open in the right mode, saving your data is as easy as using the .write method. You just give it the text you want to save, and that's it. It writes that string right into the file. Simple as that. Okay, perfect. So our data is written, it's saved on the hard drive, our program officially has a memory. But that's only half the battle, right? How do we actually read that data back into our program when we need it again?
Well, Python gives us three main tools for this job, and each one is useful for different situations. You can use read to grab everything in one go, readline to go one line at a time, or read lines to get all the lines packed neatly into a list.
So read is your get everything button. It just slurps up the entire contents of the file and hands it back to you as one single, potentially very large string of text.
Read line, on the other hand, is way more patient. It reads just the first line and then stops. Call it again, it reads the second line and stops. It's perfect when you need to process a file piece by piece, sequentially. And finally, we have read lines. This one is fantastic when you want to loop through a file. It reads every single line and packages them all up into a nice, convenient Python list for you. Each item in the list is just one line from the file.
Now, if you've looked at older Python code, you might have noticed there's always this one final manual step. After you're all done reading or writing, you have to explicitly remember to tell Python to close the file using file.close. So, what's the big deal? What happens if you forget? I mean, we're all human, right? Well, you could actually run into some nasty problems. Your data might not get saved correctly, the file could get corrupted, or you might even lock other programs out of using it. It's definitely a risk.
Honestly, forgetting to close files is a classic beginner bug. But lucky for us, Python has a much better way to handle this. It's safer, it's more professional, and it completely eliminates the problem.
Let me introduce you to the with statement. This thing is a total game changer. You use it to open a file, and the second your code inside that block is finished, Python guarantees that the file will be closed for you. No file.close needed. It's totally automatic.
Let's look at how clean this is. We're using the with statement to open marks.txt in write mode. We write a couple lines of scores, and as soon as that's done, Python just handles the closing for us. It's clean, it's safe, it's awesome.
And reading it back is just as elegant. We use with again, open the same file, but this time in read mode. We read the contents, we print them out, and again, behind the scenes, Python closes the file for us. This is 100% the way you should be doing this.
And hey, don't think this is just for text files. Not at all. By just adding a B to the mode, like RB for read binary or WB for write binary, you can use these exact same techniques to work with images, audio files, PDFs, pretty much anything.
So let's do a super quick recap of your new file handling toolkit. Everything starts with open. You've got your main modes, R, W, and A. You've got methods to read and write. And most importantly, for safe, clean, professional code, you are always going to use the with statement. So here's the bottom line. You have just learned a fundamental Python superpower. For real. You can now make your programs save data, create log files, read settings. The possibilities are endless. You've given your code a permanent memory. And just like that, you can give your programs a long-term memory. So I'll leave you with this question. Now that you have this power, what is the very first thing you are going to teach your Python program to remember?
All right, let's talk about object-oriented programming in Python, OOP. Now, I know that sounds super technical, maybe a little intimidating, but trust me, it's actually a really smart and powerful way to organize your code, to turn a tangled mess into something clean and clear. So let's dive right in. You know that feeling, right? You're deep into a project, and your code just feels all over the place.
It's like you're juggling all these different variables and functions and you're just hoping you don't drop anything. It's a super common problem, especially as your projects start to get bigger.
Well, that exact problem is what OOP is designed to solve. It gives you a structure, a master plan for everything. Seriously, just think of it like a blueprint. So instead of juggling all those loose parts, we're going to start building something solid, something that actually makes sense.
Okay, so to really get this, our first stop is understanding the difference between the plan and, well, the thing you build from the plan. The whole idea of OOP really boils down to this: the blueprint versus the actual car. So first up, we have the class. And a class is nothing more than the blueprint. That's it. It's the design, the template. It lays out all the details. You know, this car will have 4 wheels. It's going to have this type of engine. But it's not a real car yet. It's just the idea, just the plan on paper.
And that leads us to the object. An object is the real thing you build from the blueprint. It's the actual physical car you can drive. So if your car class is the blueprint, then a specific Swift or a Creta or a Fortuner, those are the objects. They're the real-world things created from that one design.
Okay, so what does this actually look like in code? It's way simpler than you might think. See this? Class student? Boom, that's our blueprint. We've just created the design for what a student is. Then this line, S1 equals student, that's us taking the blueprint and actually creating a real student object. We just brought the plan to life.
All right, so every good blueprint needs details, right? A car design needs to say what color it is, how many doors it has, and also what it can do, like drive or honk the horn. In OOP, our blueprints, our classes, work the exact same way. They have features and they have actions.
And this is the breakdown. We've got attributes, which are basically the things that describe what an object is. Think of them as nouns or adjectives, like a student's name or age. Then you've got methods, which describe what an object can do. These are the verbs, the actions, like a function to show the student's info. It really just comes down to what it is versus what it does. And here it is in the code. Inside our student class, you can see name and age. Those are our attributes. And that show function right there, that's our method. It's the action. See how everything is bundled together nice and tidy inside that one class? That's the whole point.
Okay, so we've got our blueprint, and we can make an object. But wait a minute. How do we give that new object its starting details? Like, how do we give our student a name and an age right from the get-go? Well, for that, we have something like an automatic assembly line.
This magic is handled by a special method called the constructor. In Python, you'll always see it written as __init. And here's the key part. It runs automatically. The very instant you create a new object, this method kicks in. It's the initial setup, the very first step on our assembly line.
Check this out in the code. See how when we create the student object now, we can just pass the name and age right in? That _init method grabs those values and automatically sets them as attributes for our new object. Super efficient, right? It makes sure every single object we create starts off with all the right information.
You know, car companies don't just stop at one model. They build a whole family of vehicles, right? Sedans, SUVs, trucks. They might share a basic platform, but each one has its own unique thing going on. Well, guess what? We can do that exact same thing with our code.
And this idea is called inheritance. It's really simple at its core. It just means one class can get all the features and abilities of another class. So you could have a basic car blueprint and then create a new sports car blueprint that inherits everything from the regular car, but then you can add new stuff to it, like a turbocharger.
And there are a few different flavors of this. You can have a simple parent-to-child inheritance or a whole chain of them, one after another. You can even inherit from multiple parents at once or have one parent with lots of different children. It's super flexible and powerful for reusing code.
But what if our new sports car needs a different, beefier engine sound than the standard model? That's where function overriding comes in. It's awesome. The child class can take a method it got from its parent and say, nah, I'm going to do this my own way, and provide its own special version.
This example with the animals makes it super clear. The main animal class has a generic sound method. But look at the dog class. It inherited sound, but it overrides it with its own specific version that says bark. So now, when you tell a dog object to make a sound, it doesn't do the generic thing, it barks. It uses its own specialized version.
All right, now we're getting to the really cool part, the secret sauce.
These next few ideas are what make OOP so incredibly powerful. Think of them as the advanced engineering secrets happening under the hood. First up is a big word, polymorphism. It literally just means many forms, and all it means is that the same function name, like sound, can do totally different things depending on which object you call it on. A dog sounding barks, a cat sounding meows. Same name, different actions. That's it.
Next, we've got encapsulation. Think of this as data security. It's the idea of bundling all of an object's data and its methods together in a nice, safe package, and then protecting it from the outside world. It's like tucking all the important engine wires safely inside the dashboard so you can't accidentally mess with them. This is a huge deal for preventing bugs and keeping your code stable.
And last but not least, abstraction. This one is all about simplicity. It's the art of hiding all the complicated, messy stuff and only showing the user what they actually need. I mean, when you drive a car, you just need the steering wheel, the gas, and the brake, right? You don't need to manually operate the pistons and spark plugs. That's abstraction. It gives your code a clean, simple interface so other people can use it without getting bogged down in the details.
Okay, so let's do a super quick rundown. Class is the blueprint. Object is the real thing. The constructor runs automatically when you make an object. Inheritance lets you copy features from a parent class. Polymorphism is one name, many actions. Encapsulation is about protecting your data. And abstraction is all about hiding the complexity. Got it? Good.
So there you have it. Those are the key ideas behind object-oriented programming. It's not just about syntax, it's a whole new way of thinking, a better way to structure your code. You've basically been handed the master blueprints for building amazing things. So the only question left is, what are you going to create first?
Hey everyone, and welcome. Today we're going to talk about something that really separates beginner Python code from truly solid professional applications. We're talking about handling errors, basically how to make your code bulletproof. So let's jump right in. You've been there, I've been there, we've all been there. You spend hours writing what you think is the perfect script, you hit run, and boom, it just dies. You get a whole wall of red text and everything grinds to a halt. It's super frustrating, right? Well, what if you could actually anticipate those crashes? What if you could tell your program exactly what to do when things go sideways? That's what this is all about. Today, we're going to stop being victims of our code crashing and instead become the architects of programs that just don't break. Okay, so first things first, you gotta understand that not all errors are the same. In the world of Python, they really break down into two main types. On one side, you've got your syntax errors. Think of these like typos or grammar mistakes in an essay. You forgot a colon or a parenthesis. Python is smart enough to catch these before your code even tries to run. But then you have runtime errors, or what we call exceptions. Your grammar is perfect, but when the code is actually running, something impossible happens, like trying to open a file that isn't there. These are the sneaky ones we need to plan for.
So how do we build this safety net I keep talking about? Well, Python gives us this incredibly powerful tool called the try and except block. Honestly, this is the absolute foundation of good error handling.
And it works in a really simple way. You take any code that you think might cause an error and you wrap it in a try block. You can think of this as the high-wire act. Then, right below it, you write an except block. This is the code that will run only if an error happens. That's your safety net, waiting to catch anything that falls. And here's a perfect example. We're trying to do something mathematically impossible. Divide 10 by 0. Normally, this would crash your entire program instantly. But because we put it inside a try block, Python is on high alert. The moment it sees that zero division error, instead of panicking and crashing, it just calmly jumps down to our except block and runs that code instead. The program keeps going. No crash. It's that simple. And what's really cool is you can get super specific. It's kind of like this sorting machine, right? It puts different shapes into the right bins. You can do the same thing with your except blocks. You can have one except that only catches math errors and another one that only catches file errors. It lets you handle different problems in different ways. And here are just a few of those common errors you can look out for. We've talked about zero division error, but there's also value error, which happens when you get, say, text when you expected a number, or file found error. That one's pretty self-explanatory. Knowing these specific types helps you build much smarter safety nets. All right, so try and except are like the dynamic duo of error handling, but Python gives us two more keywords that add a whole other layer of control, else and finally. Let's see how these make our safety net even better. First up is the else block. Think of this as your success code. The code inside an else block will only run if the try block finished perfectly, without any errors at all. It's the ideal place to put the stuff that should only happen when everything went right.
And then we have finally. This one is your guarantee. The code inside a finally block will run no matter what. I mean it. Whether the try block worked, whether an except block was triggered, it doesn't matter. Finally will always execute at the end. This is absolutely critical for cleanup tasks, like making sure you close a file you opened.
So let's make that super clear. Else is the celebration. It's for when the Highwire Act was a total success. Finally, that's the cleanup crew. They come in after the show is over to pack everything up, regardless of whether the show is a hit or a complete disaster.
Okay, so far we've been on defense, right? We've just been reacting to errors that Python throws at us. But what if we want to go on offense? What if we want to create our own errors to enforce our own rules? For that, we use the raise keyword.
This is where you really start taking control. Let's say you have a function that calculates something with age, and it should never, ever get a negative number. You can write an if statement to check for that. If the age is negative, you can manually raise an error yourself. This stops the program in a controlled way and sends a clear message about what went wrong.
And you can take it to the next level. You can even invent your very own custom exception types. So instead of just a generic value error, you could create a super specific invalid age error or password too short error. This makes your code so much easier for you and your team to read and debug later.
Whew, that was a lot of ground we covered. So let's do a quick fire recap of this awesome error handling toolkit you now have at your disposal.
First, you've got your try block. This is where you put any code that's a little risky, the stuff that might just fail. It's your Highwire Act.
Next, you have except. This is your safety net. When the Highwire Act goes wrong, this is what catches the fall and handles the problem gracefully.
Then there's the else block. This is your victory lap. It only runs if the try block was completed perfectly, without a hitch.
And of course, finally, your trusty cleanup crew. This code runs no matter what happens, making sure that essential cleanup tasks always get done.
And finally, the raise keyword. This is what puts you in the driver's seat, allowing you to create your own errors and enforce your own rules. Now you're in control. See, once you master this toolkit, it completely changes how you think about writing code. You're not just hoping for the best anymore, you're actively planning for the worst. You're building applications that are smarter, more resilient, and just plain better. So the only question is, what unbreakable code are you going to build first?
All right, let's dive in. Today, we're talking about the absolute essentials for doing data science in Python. We're going to take a tour through the 3 powerhouse libraries that help you turn a pile of raw information into some seriously cool insights.
So, you've got a ton of data, right? It could be anything. Sales figures, results from a science experiment, you name it. But all those numbers, they have a story to tell. The real question is, how do you find it? How do you go from a giant spreadsheet of numbers to something that actually means something?
Well, that's where Python comes in, and it's got an incredible toolkit to help you out. Think of libraries as collections of pre-written code that do all the heavy lifting for you. And today, we're focusing on the big 3, the absolute foundation for pretty much anyone working with data in Python.
First up, we've got NumPy. You can think of NumPy as the high-performance engine of our toolkit. It's all about doing math and doing it incredibly fast.
NumPy, as the name suggests, stands for numerical Python, and its secret weapon is something called an ND array. It's basically a super efficient grid that holds all your numbers, and unlike a regular Python list, this thing is built for pure, unadulterated speed.
And this slide, right here, shows you exactly why we care so much about NumPy. A regular Python list, it's kind of like a winding country road. It gets you there, but it's slower and takes up more space. A NumPy array, on the other hand, is like a superhighway. It's built for speed and efficiency. When you're working with thousands or even millions of data points, that difference is a total game changer.
And you know the best part? Getting started is unbelievably simple. You just import the library, we give it the nickname NP because everyone does, and then you create your array. Just like that, you've unlocked all that number crunching power.
Okay, so this is where the magic really happens. Look at this. You want to add 5 to every single number in that array? It's just one command. Want to double everything? Easy. Need to find the average or the biggest value in there? Bam. NumPy just does it. It's just so clean and so fast.
All right, so we've got our super fast engine for numbers.
But a bunch of numbers in a grid isn't super helpful on its own, right? They don't have any context. We need to organize them. And for that, we bring in our next tool, Pandas.
What Pandas does is it takes all that numerical power from NumPy and gives it structure. It has two main building blocks, a series, which you can just think of as a single column of data with labels, and the real star of the show, the data frame. A data frame is basically a whole table with rows and columns, just like a spreadsheet you'd see in Excel.
Now, a lot of the time, your data might start out looking a little messy, maybe something like this, a standard Python dictionary. It works, but it's not exactly easy to read or analyze, especially when it gets a lot bigger.
And boom, look at that. This is the magic of Pandas. With one simple line of code, it takes that messy dictionary and turns it into this beautiful, clean data frame. Now we've got labeled columns, we've got rows, we can instantly see who got what mark. This is where real data analysis can finally begin.
And Pandas is an absolute workhorse. It can pull data straight from a file like a CSV, it lets you save all your cleaned up work, and it gives you these amazing shortcuts like .head to just peek at the first few rows, or my favorite, .describe, which gives you a whole statistical summary of your data in a single command. It's fantastic.
So, we've crunched the numbers with NumPy, we've organized them into a neat table with Pandas. Now for what I think is the most fun part, telling the story behind the data. And for that, we need our third tool, Matplotlib.
Matplotlib is kind of like the original, the granddaddy of plotting libraries in Python. Its whole reason for being is to turn your organized data into visual insights. You know, the charts and graphs that our brains are just so much better at understanding than a table full of numbers.
For example, say you want to see how something changes over time, a line plot is perfect. And check out how simple the code is. You just give it your X and Y points, tell it to plot, and Matplotlib does the rest, giving you a really clean graph.
What if you need to compare different things against each other? Maybe sales for product A versus B versus C. A bar graph is your go-to. And again, look at that code. It's so intuitive. You give it the labels, you give it the values, and you get a perfect bar chart.
And of course, if you want to show how different carts make up a whole, like how a budget is split up, the classic pie chart is a great choice. And yep, you guessed it, Matplotlib makes it incredibly easy to create one.
Okay, so let's zoom out for a second and see how these three amazing tools fit together. Because they're not just separate things, they form a complete workflow for just about any data project.
It's a really logical flow, right? You start with NumPy, your engine, to do all the fast math on the raw numbers. Then you pass that over to Pandas, the organizer, to put everything into a nice, clean, structured table. And finally, you give that beautiful table to Matplotlib, our storyteller, which turns it into a picture that actually tells you something important.
And this really sums it all up. Look, there are tons of other data science libraries out there, but these three, NumPy, Pandas, and Matplotlib, they are the absolute foundation. They are the bedrock that almost everything else in the Python data world is built on.
So, there you have it. You've got the engine to calculate, the organizer to structure, and the storyteller to visualize. The only question left is, what story is your data waiting to tell?
Hey there. So you want to unlock the power of data in Python, but you're not quite sure where to begin? You are in exactly the right place. Over the next few minutes, we're going to build your essential data toolkit from the ground up, giving you the skills to handle real-world information. Let's dive in. You hear the word data thrown around everywhere, right? It powers pretty much every app, every website, every business. But here's the thing. All that data is pretty useless unless you know what to do with it. So how do you take all that raw information and actually make it useful inside a Python script? Well, that is the exact question we are tackling today. Here's our game plan. First, we'll get the lay of the land of the data world. Then we'll add two absolutely crucial tools to our toolkit, working with CSV files and JSON data. After that, we'll put those tools to work with some basic analysis. And finally, we'll wrap it all up into your brand new Python data toolkit. Okay, to get started, we're not going to try and cover every single obscure data format out there. Nope. Instead, we're focusing on the two most common, most essential formats you will run into day after day. You master these two, and you are ready for almost anything. First up in our toolkit is the humble, but honestly incredibly powerful CSV file. The easiest way to think about a CSV, just picture a digital spreadsheet that's been stripped down to its bare essentials. The name really says it all. Comma, separated, values. It's just a text file where each line is a row, and the different values in that row are, you guessed it, separated by commas. It's the universal language for table-based data. And this shows it perfectly. You've got a name column, a marks column, and then you have rows for each student. This simplicity is its superpower, because it means that pretty much any program, from Excel to a custom script, can understand it instantly. Now, just watch how simple Python makes this. We're going to use a library called Pandas. It's the absolute standard for data work for a reason. In step 1, we just import it. In step 2, we use one command, pd.readcsv, to load the entire file into a special structure called a data frame. Just think of a data frame as a supercharged spreadsheet living right inside your code, ready for you to work with. It's really that easy. And going the other way is just as straightforward. Once you've manipulated your data, you can save it back out with one command, df.toCSV. And here's a little pro tip. Adding index equals false tells Pandas not to write out the extra row numbers, which just keeps your final output file nice and clean. All right, on to our second tool. If CSV is the digital spreadsheet, you can think of JSON as the native language of the internet. When your app fetches data from a server or you connect to a web API, you are almost certainly speaking JSON. So JSON stands for JavaScript Object Notation, and its superpower is storing data in key value pairs. Think of it like a business card. The key is the label, like name, and the value is the actual information, like Aman. Here is a perfect example. We have the key name paired with the value Aman, the key age paired with 12, and so on. It's structured, but it's also really flexible, which is exactly why the web loves it so much. And just like with CSVs, Python makes this incredibly easy. First, you import the JSON library, which is built right into Python, so nothing to install. Then, you use json.load to pull the data into a Python dictionary. And a dictionary is just Python's name for a collection of key value pairs, a perfect match for JSON. Writing JSON is just as simple. You use json.dump. And here's another great tip. Adding indent equals 4 formats the output file with nice spacing, making it so much easier for you or anyone else to actually read it. So here's the key takeaway. It is all about choosing the right tool for the job. If you see data that looks like a spreadsheet with all these neat rows and columns, you're going to reach for CSV and Pandas. But if you see data that's structured more like a document with nested information and descriptive labels, well, that's a job for JSON. All right, we've loaded our data. We have the raw material. Now for the fun part, putting our tools to work to actually ask questions and get answers. Let's power this thing up. We'll use this simple student data set that we've loaded into a Pandas data frame. We've got 3 students and their marks. Let's see what we can find out. Want to know the top score in the class? It's just one line of code. We simply select the marks column and call the .max method on it. And boom, Python tells us the highest score is 90. How about the class average? Is the class doing well overall? Again, one simple, intuitive command, select the marks column and call .mean. And just like that, we have our answer. What if we want to create a leaderboard? Easy. We use sort_values, tell it to sort by the marks column, and then we specify ascending equals false, which is just a fancy way of saying put the highest score right at the top. Now, this one is one of my favorites, filtering. Let's say we only want to see the students who scored above 80. This line of code is like asking Python a question directly. Hey, show me the rows for my data where the value in the marks column is greater than 80. Powerful stuff. And there you have it. In just a few minutes, you've added some incredibly powerful and practical skills to your programming toolkit. Let's do a quick recap of what you've learned. Think of this as your new cheat sheet. When you see tables, you know to use CSV and Pandas. When you see that nested web data, you've got JSON. And when you need to ask questions to find the highest value, the average, or to sort and filter your data, you now know that Pandas is your go-to tool. These fundamentals, they're the bedrock of data work in Python. So we'll leave you with this thought. You now have the fundamental tools to read, write, and analyze the most common types of data out there. The only question left is, what will you build? What questions will you answer? What story will you tell with data? Thanks for watching. All right, let's talk about a skill that's absolutely essential for any Python programmer, handling files. This is the secret sauce that lets you give your code a memory, so it can actually remember things long after you've closed the program. So let me ask you this. Have you ever spent, I don't know, a couple of hours building a cool little program, maybe a to-do list or a simple game, only to have it forget everything the second you shut it down? You know the feeling, right? It's kind of a classic coding moment. You run your code, it works like a charm, you get that little burst of, yes, I did it. And then you close the window and poof, it's all gone. Just vanished into the ether like it never even happened. So what's actually happening here? Well, your program is using what's called temporary memory, or RAM. Just think of it like a sticky note. It's useful for jotting things down right now, but once the program ends, that sticky note gets crumpled up and thrown away. The solution? Permanent memory. By saving data to a file, we're basically taking the info off that disposable sticky note and writing it into a permanent notebook. We're giving our code the power to remember. Okay, so let's dig into that first part a little more. Section 1. Why does your code have such a bad memory? So yeah, we're done with forgetful programs. It is time to learn how to store that data for good. It's time to give our code the power to actually, finally, remember. Which brings us to Section 2. How do we actually do it? How do we give our code a memory? Our entire journey into file handling starts with this one simple function, open. I want you to think of it like the key to a file cabinet. You can't see what's inside, and you definitely can't add new stuff until you unlock it. This little command is your key. It's the gateway to everything else. Now, once you've used your key to open the file, you have to tell Python what you actually want to do. And for that, there are 3 main modes, or as I like to call them, the 3 magic words. First up, we've got R for read mode. And honestly, the slide says it all. You can look, but you can't touch. This is your safest option. It's perfect for when you just need to grab some data from a file and you want to make sure there's 0 chance of accidentally messing anything up. Next is W for write mode. And you really need to pay attention to this one. This is the one with the big warning label. Using W is like grabbing a brand new, totally blank sheet of paper. It completely wipes out everything that was in the file before. So, bottom line, only use this when you mean to start completely from scratch. And that brings us to our 3rd magic word, append mode. This is write mode's much friendlier, safer cousin. Instead of wiping the slate clean, it just quietly goes to the very end of the file and adds your new stuff, leaving all the old content untouched. This is perfect for things like adding a new entry to a log or a diary. Now, R, W, and A are the big 3 you'll use 99% of the time. But this table here gives you the whole picture. You'll see some other modes like X, which is a cool, safe way to create a new file only if it doesn't already exist. And we'll talk about that B for binary files, for things like images, in just a little bit. For now, just think of this table as a handy reference sheet. So we know the basic commands now. But it turns out there's kind of an old way of doing things and a much, much better, smarter way. So in this section, let's focus on the modern best practice. It's all about working smarter. And this slide just lays it out perfectly. The old way, over on the left, is totally manual. You have to remember to type f.close at the end. And if you forget, or what if your program crashes before it gets to that line? You can end up leaving files open, which can cause all sorts of problems. But the method on the right, the with open statement, that's the automatic and way safer way to go. And the real beauty of this modern approach is that Python just handles all the cleanup for you. It guarantees that the file will be closed properly no matter what, even if your code hits an unexpected error. The second your program exits that indented block of code, Python steps in and closes the file. It's cleaner, it's safer, and it is absolutely the way you should be working with files today. Okay, so we've got a handle on opening and closing simple text files. But what about when the data gets a little more, complex? In this next section, let's go beyond just simple text and really expand our toolkit. So what if you have something like a Python list, maybe a shopping list? Well, you can't just write the whole list object in one go. The process, like you see here, is to loop through it. You open the file, you go through each item in your list one by one, and you write them to the file. And you'll usually want to add a little new line character at the end of each one so they don't all just get smooshed together on one line. And hey, this isn't just for text. What about images, audio files, that kind of thing? The principle is exactly the same. You just add a B to the mode for binary. So RB lets you read a binary file, and WB lets you write one. You can actually build a simple program that copies an image file using just those 2 commands. It's pretty cool. Now this brings up a more advanced but super useful idea, the file pointer. The easiest way to think about this is like the blinking cursor you see in a text document. The tell command, well, it tells you where that cursor is. The seek command lets you jump that cursor to any spot you want, and then any read command you use will start reading from that new position. This gives you amazing control over exactly where you're reading from or writing to inside a file.
Okay, you've learned the theory, you know the modes, you know the best practices. So for our final section, let's put it all together and see what you can actually build with these new powers. Let's tackle something simple but really practical, a program that asks for a student's name and their grade and saves it to a file. This is a perfect little real-world example that uses everything we've just talked about.
And the logic couldn't be simpler. Step 1, ask the user for a name. Step 2, ask them for the marks. And step 3, open a file in append mode, remember, A, so we don't erase the old entries, and just write that new record to the file. That's it. Simple, powerful, and it creates a permanent record.
And that little student project is really just the tip of the iceberg. I mean, think about what you can build now. You can create log files to see what your program is doing. You could build your own diary app. You could save high scores for a game you're making or store user preferences. The possibilities are suddenly huge.
You've just unlocked one of the most fundamental parts of programming, giving your applications a memory. You now have the tools to build that log file, that diary app, or a simple student database. So I'll just leave you with one question. What are you going to build first?
Hey there, and welcome. If you've ever been curious about coding but got kind of bogged down by all the theory, you are in exactly the right place. Today, we're ditching the boring lectures and jumping right into the fun stuff, actually building things.
You ever use an app on your phone and think, hey, I bet I could build something like this? Well, the answer is, yeah, you totally can. And we're going to look at how you can take that very first step.
And you know what? We're going to prove it, right here, right now. We're going to blast through the blueprints for 5 complete Python projects. Think of it as your own personal coding launchpad. So let's kick things off with something you probably use every single day.
All right, first up, the good old calculator. This is like the perfect first project. Why? Because it's something we all get, it's super practical, and it's an amazing way to learn some of the absolute core ideas of programming.
So our calculator is going to do the big 4, adding, subtracting, multiplying, and dividing. The whole idea is simple. The user gives us 2 numbers, tells us what to do with them, and boom, we spit out the answer. It's the perfect little example of a program that takes input, does something with it, and gives you an output.
Okay, so the magic behind this whole thing is something called conditional logic. That's just a fancy way of saying we're teaching the computer how to make a choice. Just look at this line of code right here. The if statement is just checking what the user picked. If they chose 1 for addition, then it runs the code to add the numbers. This is a fundamental, must-know building block for any program.
And from the user side, it's totally smooth. You type in your numbers, pick what you want to do, and bam, you get the answer right away. And just like that, we've got a tool that can follow instructions and give back a specific result.
Okay, so we've built a useful tool. That's cool. But you know what's more fun than math? Games. Let's take that same if this then that logic and make something playful. And that brings us to project number 2, the quiz game. We're going to take that exact same decision-making logic from the calculator, but instead of checking for math operations, we're going to check for right answers and keep score.
The game itself is super simple. It asks 5 multiple-choice questions. After each one, it'll let you know if you got it right, and then at the very end, it'll tell you how you did. It's all about making something interactive and fun.
And the code behind it? It's just as simple. Remember how our calculator used an if statement? Well, same deal here. This line checks if the player's answer is A. If it is, boom, we add 1 to the score. We're using the exact same concept for a completely different result.
All right, project number 3. Let's flip the script a little bit. This time, you're not answering the computer's questions. You're trying to figure out its secret. We're building a number guessing game.
So the computer thinks of a secret number, and your job is to guess what it is. But here's the cool part. The thing that makes it a real game, the feedback. The program doesn't just say, nope, you're wrong. It actually helps you. It gives you hints, telling you if your guess was too high or too low.
Now, this project introduces a really powerful new idea. The loop. See that while true? That's basically telling the computer, hey, keep doing this thing over and over again until I tell you to stop. It's what keeps asking for guesses and keeps the game running until you finally win.
So the way you play is super simple, but it's really addictive. The computer has a secret. You guess. And the game's hints, too high, too low, push you in the right direction. It's a perfect mix of the decision-making we've already seen and this new, powerful loop.
Okay, so we've made tools, we've made games, now let's get serious and see how code can actually talk to the computer itself. Project 4 is a file manager, and this is like building your own little mini operating system.
Now this is a huge step up. With this thing, you can literally tell your computer, hey, create a new file for me, or read what's inside this one, or even get rid of this file, I don't want it anymore. This is some real-world power right here.
The user is completely in the driver's seat here. You pick what you want to do, create, read, or delete, tell it which file, and the program makes it happen. It shows you just how powerful code can be for automating stuff on your own machine.
Okay, for our last project number 5, we're going to do something super practical, something you see all the time in the real world, processing data. We're building a program that generates a student report card. It's going to take a bunch of raw numbers and turn them into a nice, clean report.
So here's how it works. You give the program the raw data, right? A student's name, their grades in different subjects. And then the program does all the heavy lifting. It crunches the numbers, calculates the total, figures out the percentage, and even assigns a final letter grade.
And this is the logic it uses to assign those grades. It's just a chain of if this, then that statements. That elif you see, it's just a shortcut for else if. The program checks the percentage against the first rule, then the second, then the third, until it finds the right grade.
But it all comes down to this one simple calculation. This one little line of code takes the total score, divides it by 5, and poof, you've got the percentage. That one number drives the entire grading system.
And there you have it. In just a few minutes, we've sketched out the blueprints for 5 totally different but totally functional apps. We went from a basic calculator all the way to a program that processes data.
But honestly, the projects themselves aren't even the most important part. Look at the core concepts we've just unlocked. We've covered how to get input from a user, how to store data, how to make decisions with if-else logic, how to repeat things with loops, and even how to manage files on your computer. These 5 things, they are the absolute bedrock of pretty much any program you could ever dream of building.
So, you've seen what's possible. You've seen what you can do with just a handful of simple ideas. The foundation is there. The only real question left is, what are you going to build next?
All right, let's get right into it. Think you've got a good handle on Python? Well, we're about to put that to the test. Welcome to the Python Pop Quiz. So yeah, this is your chance to really show what you know. No pressure, of course, but let's see how you do. Ready to jump in? Okay, let's kick things off with round 1, rapid fire basics. We're talking about the absolute fundamentals here. I'll throw them out, you think of the answer. Let's do this. All right, question number 1. You're writing some code and you want to leave a little note for yourself, something the Python interpreter will just totally ignore. What's the one symbol you use to do that? Got it in your head? Let's see. That's right, it's the hash symbol. Anything on a line that comes after that little die is completely invisible to Python. It's the perfect way to leave notes for your future self or, anyone else reading your code. Okay, moving on. Next question for you. If you type out len, and then in parentheses the string hello, what's the output going to be? What number does that super common function spit out? And the answer is 5, of course. The len function is one you'll use all the time to get the length of stuff, like strings, lists, you name it. HELLO, yep, that's 5 characters. Okay, time for a little history lesson. A little trivia for you. Python was created by who? Can you fill in that blank? Who's the person behind this amazing language? That would be the one and only Guido van Rossum. He's the Dutch programmer who first cooked up Python way back in the late 80s. A true legend in the open source world. All right, let's switch it up. True or false? Python is case sensitive. What do you think? The answer is true. And this is a really big deal. A variable named my_var with a lowercase m is totally different from one named my_var with a capital M. You gotta watch out for that. Okay, last one for the rapid fire round. True or false? A tuple is mutable. And that is false. Remember, tuples are immutable. That means once you make one, you can't change it. It's locked in. That's the whole point, and it's what really separates them from lists. Great job on the basics. You're warming up now. So let's move on to round 2, core concepts. We're going to dig into some of the ideas that really make Python tick. So first up, what even is a variable? Well, the simplest way to think about it is like a labeled box. It's a container in your computer's memory where you can store stuff. In this example, we've got a box labeled name, and inside we've put the string R of. Super simple, right? And functions? What are they all about? Well, a function is basically a block of code that you can wrap up, give a name to, and then use over and over again. You define it once with that def keyword, and then you can just call its name whenever you need it. It's an absolutely essential tool for keeping your code from becoming a messy, repetitive nightmare. All right, let's talk about a classic Python question. What's the difference between a list and a tuple? It really boils down to two things. First, lists are mutable. You can change them. Tuples are immutable. They're set in stone. And second, the syntax. Lists use those square brackets, while tuples use parentheses. That's the core of it. Okay, theory is one thing, but can you put it into practice? Welcome to round 3, the coding challenge. This is where we stop just talking about code and start thinking about how to actually write it. So here's the first challenge for you. Let's say I give you any sentence, any string of text. How would you write a little program to count up all the vowels in it? You know, A, E, I, O, and U. Just take a second. How would you even start to tackle that? Okay, let's think through the logic, step by step. First, you're going to need a counter, right? Let's just start it at 0. Then you need to go through the string character by character. That sounds like a loop. And for every single character, you've got to ask a question. Hey, are you a vowel? If the answer is yes, you just add 1 to your counter. Make sense? And this is what that logic looks like as actual Python code. See? We set count to 0. We use a for loop to go through each character. Then that if statement is our question. It checks if the character is inside that string of vowels. And notice we check for both lowercase and uppercase, which is important. If it is, count plus equals 1. Boom, done. Simple, but it works perfectly. All right, let's level up a bit. This next one is about object-oriented programming. So how would you create a class, which is really just a blueprint for a student? And this blueprint needs to hold 2 pieces of information for every student, their name and their marks. So how do we do it? First, you just use the class keyword to say, hey, I'm making a blueprint. Then inside, you create this special underscore init method. Think of it as the setup instructions that run every time you create a new student. It always takes self first, which is just a way of referring to the student object itself, and then the other things you want to store, like name and marks. Then you just tell it, okay, take the name you were given and attach it to this student object. And once that blueprint is made, you can start creating actual student objects from it. And here's the code. It's pretty straightforward when you see it. We define our student class. There's our underscore init method taking self, name, and marks. And those 2 lines, self.name equals name and self.marks equals marks, are where we're actually attaching the data to the object. Then at the very end, look, we create a new student, S1, using our blueprint, and we pass in Ria for the name and 94 for the marks. Wow, you made it through the coding challenges. You're almost at the finish line. It is time for our final bonus round, Lightning MCQs. This is going to be fast, so get ready. Okay, no time to waste. What's the type of 5.0? It's a float, because of that decimal point. What brackets for a dictionary? The curly ones. Does the number 3 equal the string 3? Nope, that's false. They're different types. What does R mean when you open a file? Read mode. And last one, a class is a what for objects? It's a blueprint. So how'd you do? And that's it. That was our Python pop quiz. Hey, whether you got every single one right or maybe learned a thing or two, what matters is you're getting comfortable with the fundamentals of an awesome programming language. So now the real question is, with this knowledge, what are you going to build next?